Welcome to Omni Eyes. Today, we explore the incredible macro vision of the weevil, a tiny master of absolute precision targeting. Look closely at this fascinating creature. Its unique visual system is completely optimized for tasks requiring unbelievable exactness and extreme focus. Unlike most insects, the weevil has its eyes positioned directly on the sides of its elongated snout, creating specialized viewing angles. To this tiny insect, a simple green leaf appears as a vast, complex landscape of microscopic ridges and very deep valleys. Before drilling into the plant, the weevil must carefully measure the surface. It uses its specialized eyes to scan the cellular structure. This remarkable biological process is known as macrovision. The insect achieves an incredible level of detail at an extremely close range. Instead of capturing a wide panoramic view, the weevil utilizes a very narrow field of view to concentrate on specific target areas. By sacrificing peripheral awareness, this incredible creature can focus its entire visual processing power onto a single, microscopic point of absolute interest. We call this unique biological strategy precision targeting. It allows the tiny insect to operate with an accuracy measured in exact micrometers. Imagine a highly sophisticated camera lens that ignores the surrounding environment to lock entirely onto one specific, crucial detail with absolute perfection. The weevil snout is not just a simple feeding tube. It is a highly advanced sensory apparatus equipped with specialized optical sensors. These optical sensors gather precise topographical data from the plant's surface, sending immediate feedback directly to the tiny brain of the insect. Every microscopic bump and tiny ridge is carefully analyzed. The weevil calculates the exact optimal location for its impending drilling operation immediately. At the very tip of the long snout lie the mandibles. These sharp tools act as the biological drill bits for excavation. Guided by the intense macrovision, the mandibles begin to chew through the tough outer layer of the green plant leaf systematically. The precision is truly astounding. A single millimeter of error could mean failing to reach the vital nutrients hidden deep within tissues. Notice how the insect remains perfectly still during this critical phase. All its energy is channeled into maintaining a steady visual lock. This visual lock is the cornerstone of precision targeting. It eliminates all unnecessary background noise, ensuring complete focus on the primary objective. In the realm of nature, efficiency is survival. The weevil cannot afford to waste precious brain power on irrelevant visual data processing. By restricting its field of view, the insect creates a highly efficient neural pathway, dedicating 100% of resources to drilling. Let us compare this biological marvel to modern human technology. How do our advanced machines replicate this level of extreme micro-precision? Traditional cameras are designed to capture as much of the scene as possible. They prioritize broad awareness over incredibly fine, targeted detail. However, in highly specialized fields like remote robotic surgery, a broad panoramic view is often completely useless, and sometimes even dangerously distracting. A surgeon operating a remote robotic arm needs absolute clarity on a tiny, specific area of the human body to perform safely. This is exactly where the concept of the weevil eye becomes revolutionary. Engineers are now designing medical cameras based on this principle. These bio-inspired surgical cameras feature a deliberately narrow field of view, focusing all digital resolution onto a single critical surgical incision point. Just like the tiny insect drilling into a leaf, the robotic surgical tool locks onto its target with unparalleled, extreme microscopic accuracy. By eliminating visual distractions from the periphery, the medical system can process the central image faster and with much greater overall clarity. This precision targeting approach dramatically reduces the cognitive load on the human surgeon, allowing for safer and more successful complex medical procedures. The applications of this remarkable macrovision extend far beyond the operating room. Let us explore the fascinating world of microelectronics. Modern computer chips are incredibly dense, packed with billions of microscopic transistors that are completely invisible to the naked human eye today. Inspecting these tiny, complex circuit boards for manufacturing defects requires a visual system capable of extreme magnification and absolute, unwavering focus control. Once again, the weevil provides the perfect natural blueprint. Industrial inspection cameras now utilize narrow-field lenses to scan for microscopic flaws. These specialized cameras lock onto individual solder joints, analyzing them with the same intense scrutiny a weevil applies to a green leaf. If a microchip contains a single faulty connection, the precision targeting camera will detect it instantly, preventing a potential catastrophic system failure. The software powering these industrial cameras mimics the neural pathways of the insect, dedicating maximum processing power to the small targeted zone. This allows factories to inspect millions of tiny electronic components rapidly, ensuring high-quality control without sacrificing the crucial microscopic detail required. It is truly fascinating how a humble bug from the forest can directly inspire the manufacturing processes of our most advanced computers. To fully appreciate this biological connection, we must dive deeper into the specific anatomy of the weevil eye and its optical structure. The compound eye of this insect is composed of numerous tiny lenses called ommatidia, each functioning as an independent light-sensing unit. However, unlike a fly that sees a wide mosaic, the weevil ommatidia are densely packed and angled forward to create overlapping fields. This unique forward angling creates a concentrated zone of high resolution directly in front of the snout, perfect for precise drilling operations. Think of it like holding two magnifying glasses together. The focal point becomes incredibly sharp, while the surrounding edges blur into nothingness. This deliberate blurring of the periphery is a biological feature, not a flaw. It forces the insect brain to ignore useless distractions. When the weevil prepares to drill, its microscopic world narrows down to a tiny, highly illuminated circle of extreme clarity and focus. The mandibles then move into this circle of clarity. The insect essentially guides its tools using a built-in, high-powered microscope. As the drilling commences, the eyes continuously monitor the depth and angle of the hole, making microscopic adjustments in real time, constantly. This continuous feedback loop between the macro vision and the physical mandibles is a masterpiece of natural engineering and evolutionary biological design. Let us observe the drilling process in slow motion. Notice the incredible stability of the insect head as the sharp jaws work. Every tiny movement is calculated. Every microscopic bite is guided by the unyielding focus of those specialized, side-mounted, highly perceptive eyes. The hole gets deeper, perfectly cylindrical, and exactly wide enough to access the soft, nutrient-rich plant tissues located beneath the surface. This flawless excavation is only possible because the insect visual system refuses to be distracted by anything outside its immediate target zone. Now, let us shift our perspective back to the human world. Think about the challenges faced by engineers designing autonomous targeting systems. Autonomous drones and robots often struggle with visual overload. Processing a wide field of view requires massive computational power and huge batteries. When a drone needs to perform a delicate task, like inspecting a power line or repairing a tiny sensor, broad vision fails. The drone becomes confused by background movement, changing light conditions, and irrelevant objects in the surrounding environment, leading to critical operational errors. By adopting the Weevil strategy of precision targeting, engineers can equip drones with secondary, narrow-field cameras dedicated solely to specific tasks. The main camera navigates the drone, while the precision macro camera locks onto the target, ignoring the wind, swaying trees, and clouds. This dual camera system mimics the evolutionary brilliance of the insect world, combining general spatial awareness with intense, highly focused task execution. The result is a robotic system that is faster, more accurate, and significantly more energy efficient, all thanks to a tiny bug. Let us journey back into the microscopic forest. The weevil has successfully penetrated the tough outer layer of the green plant leaf. Now it must extract the nutrients. Even during this feeding phase, the macro vision remains actively engaged, monitoring the internal plant structure. The insect uses its vision to identify the richest veins of sap, navigating the internal microscopic labyrinth with absolute confidence and precision. It is a remarkable display of biological coordination. The eyes, the brain, and the mandibles work together in perfect, seamless, microscopic harmony. Scientists studying this behavior are continually amazed by the efficiency of the neural processing involved in maintaining such a narrow visual lock. They have discovered that the weevil brain actually suppresses signals from peripheral optical sensors entirely when the central targeting system is active. This active suppression is a sophisticated form of neural filtering. It prevents sensory overload and guarees absolute concentration on the vital task. Imagine applying this active neural filtering concept to artificial intelligence systems used in modern self-driving cars or advanced autonomous navigation vehicles. A self-driving car must process massive amounts of visual data constantly. This requires heavy, expensive computers and consumes significant electrical power. If the AI could learn to suppress irrelevant background data dynamically, focusing only on critical targets like pedestrians, efficiency would skyrocket immensely. The Weevil teaches us that sometimes seeing less is actually seeing more. True precision requires the intelligent elimination of unnecessary visual noise. This philosophy of intelligent elimination is reshaping how optical engineers design lenses for scientific instruments, microscopes, and deep space exploration satellite cameras. In deep space, a satellite looking for a tiny exoplanet must ignore the blinding light of nearby stars to lock onto darkness. By employing narrow field targeting principles inspired by our tiny insect friend, astronomers can filter out stellar glare and spot hidden worlds. From the microscopic surface of a green leaf to the vast, dark expanse of the universe, the principle of precision targeting remains. The Weevil has mastered this principle over millions of years of evolution, surviving and thriving through its incredible ability to focus intensely. As we observe the insect finishing its meal, we can see the mandibles retracting and the snout pulling away from the leaf. The perfectly round hole left behind is a testament to the flawless execution of macrovision and biological precision targeting in nature. The insect now pauses, its specialized eyes scanning the immediate area for predators, before moving on to find its next potential target. Even in this scanning mode, the narrow field of view dictates its behavior. It must turn its entire head to see around. This head-turning movement is deliberate and robotic, a direct result of having eyes optimized for forward-facing, microscopic depth perception tasks. Every aspect of the Weevil anatomy is a specialized adaptation, proving that nature is the ultimate engineer of highly functional, targeted systems. We often look to massive animals for inspiration, but the microscopic world holds secrets that are equally profound and technologically revolutionary today. The next time you see a tiny bug on a leaf, remember the complex visual processing and precision targeting happening within it. It is not just wandering blindly. It is calculating, measuring, and executing complex physical maneuvers with an accuracy we can barely comprehend. Biomimicry, the science of copying nature, relies heavily on detailed observations of these microscopic marvels to solve complex human engineering problems efficiently. By understanding the Weevil eye, we are learning how to build better cameras, safer surgical robots, and more efficient artificial intelligence networks. The bridge between biology and technology is built upon these tiny, often overlooked details found in the deepest corners of the forest. Imagine a future where our surgical tools are entirely guided by artificial Weevil eyes, ensuring every incision is absolutely perfect and safe. Imagine industrial manufacturing lines where microscopic flaws are instantly detected and corrected by optical sensors, mimicking the intense focus of this insect. This future is rapidly approaching, driven by our growing understanding of macrovision and the undeniable power of biological precision targeting systems. We must continue to protect and study these natural environments, for they hold the blueprints to our own future technological advancements, always. The humble Weevil, with its strange snout and side-mounted eyes, is a tiny masterclass in optical engineering and focused neural processing. It reminds us that evolution does not waste energy. Every physical trait serves a highly specific, perfectly optimized purpose for ultimate survival. By narrowing its vision, the insect expanded its capability to interact with the microscopic world in a profoundly accurate and successful manner. The concept of macrovision challenges our traditional understanding of sight. It proves that limitation can sometimes be the greatest evolutionary advantage. As we develop more advanced visual technologies, we will undoubtedly continue to draw inspiration from the precise, unwavering gaze of the Weevil. From the dense jungle canopy to the sterile environment of a modern operating room, the legacy of this tiny insect vision lives. It is a beautiful reminder of the interconnectedness of all scientific disciplines, blending biology, optics, robotics, and artificial intelligence into one narrative. We've explored the anatomy, the biological mechanics, and the incredible technological applications of this fascinating creature and its highly specialized eyes. The weevil stands as a microscopic monument to the power of extreme focus and the absolute necessity of precise, targeted visual measurement. Its narrow field of view, once thought to be a limitation, is now recognized as a brilliant evolutionary strategy for survival excellence. We hope this deep dive into macrovision has changed how you perceive the tiny, complex world of insects surrounding us completely. Nature always provides the most elegant solutions to our most complex engineering problems, waiting patiently for us to observe and learn closely. Thank you for joining us on this incredible microscopic journey today. Until next time, keep exploring the hidden wonders with Omni eyes.